The purpose of this video is to go over the homework for regression. We're going to start with the vision data set. So load up that guy. Then we are going to, let's see if we can find the data right there. And let's look and see what we have. So there are 15 questions in this workshop. Number 1, select the data where init years equals 0. Now, the vision data set is basically comes from the CLEAR study, and there are myopes and hyperopes and emmetropes and so forth. Actually, I also define extreme myopes and extreme hyperopes. But we're going to use the variable init years. Now, init years is the years before and after and including the year of diagnosis for myopia. So if we select based on this variable, we will only get myopes. So we're going to go to select cases and let's try that again. Data. And we're going to set our condition to if condition is satisfied, if init years equals 0. So that means that this is the year the child was diagnosed with myopia. So init years equals 0. And then when we look at our output data view, we see right here, this is subject 1500 and init years is 0, but everybody else has an X is slashed out, so we're just getting this row. This first person happened to be an extreme myope. But no emmetrope didn't get picked. Notice emmetropes don't have any data in init years. So that's your first task. How many subjects are there? We could go analyze descriptive frequencies, and we can just look at visit. Doesn't really matter what we look at. We see we get 295 subjects. And they were anywhere between visit 1 through 6. There's also a visit 0. People were not included, or no, I guess that's the first year. We don't look at years before. Everybody starts out at not having myopia, so their first year, or their first visit, actually, I'm sorry, this is visit. That is year 1, not init visit. Okay. So question number 2. Analyze correlation to create a correlation matrix with the variables. Now, we did something like this the other day. This is kind of an interesting thing. If we look at our variables, we have cylinder. No, sorry. This is a different one. We have, we want to do, we're going to ultimately do mean axial length. Let's see. We have these 4 variables. Vitreous chamber depth, anterior chamber depth, mean lens thickness, mean axial length. Let's look at our correlation matrix. You see that if we look at mean axial length, the one most correlated is vitreous chamber depth. That's because that's probably the longest one. Anterior chamber depth is next, And oddly enough, mean lens thick. The thicker the lens, that makes kind of sense. Think about this as a myopic. The thicker their lens, the shorter their mean axial length. Because what's happening is their axial length is growing, their mean axial length is thinner. So a mean lens thickness of the more thick it is, the shorter their axial length probably is. Has much more way to grow. All right, let's number 3. What proportion of the mean axial length variance is accounted for by these? Well, what we would do for that is just copy this. Let's try that again. Correlations. What did I do? Copy this and go into, let's make a, actually this is what I had done a minute ago. Paste, paste, and what it asks for is what proportion of mean axial length is accounted for by VCD. Proportion is r squared, and we have the r's here. So we would take each of these values equals that, whoops, not there, down here at mean axial length. And so let's take equals this value squared. Now this isn't going to work, so what we have to do, get rid of those little stars. So 89% of the variance of axial length is accounted for by vitreous chamber depth. Let's wrap our text. And then this one is just copy these. And we have to get rid of the asterisks. So we see that 5% or 8% of the variance is accounted for, of mean axial length is accounted for by anterior, and then 5% is shared there. All right, let's go. The next question is, do VCD, ACD, LT account for a clinically relevant amount of variance according to our rule of thumb? Our rule of thumb says r squared has to be greater than 0.1. So, oops, where was that? So who is above 0.1? Only vitreous chamber depth. These others are kind of small for using our r squared measure. Actually, okay, the next one is run an analysis regression model with mean axial length as a dependent, oh actually that's spherical equivalence. No, mean axial length. Sorry, getting ahead of myself. Run a regression with mean axial length as a dependent variable and vitreal chamber depth, anterior chamber depth, and lens thickness as the independent variables. So here we go. Vision data, analyze, regression linear. Let's reset this old one. So our dependent variable is mean axial length, and vitreous chamber depth and mean lens thickness are independent variables. And what we can do, things you should normally do, is for under these statistics, it's always good to do collinearity diagnostics, and it's also sometimes useful to save unstandardized residuals. So that's under Save Unstandardized Residuals, Statistics, Collinearity. Okay. Now look, we got a warning. It says for the final model with dependent variable mean influence statistics cannot be computed because the fit is perfect. Look at this, our R squared is we've accounted for 100% of the variance. Can't even compute a p-value for that. The vitreous chamber, anterior chamber depth, the mean lens thickness, all their coefficients are 1. The constant is pretty close to, as close as you can get to 0. The tolerance shows that they all are pretty much accounting within each one for all the variance. Inflation factors are well below 2. And we're going to ignore the collinearity doctrine. And it did calculate residual statistics. And but for this program, it doesn't matter quite so much. So what does this tell us? This tells us that the people who created the data did not actually observe all 4 of those measures. They observed 2 of them, or 3 of them, and calculated the 4th. Now, I don't remember which one it was they calculated, but I'm pretty sure it was vitreous chamber depth, though it could have been anterior chamber depth. But it's perfect because the coefficients just, in real life, things are not perfect, and you don't account for 100% of the variance. In this case, you do because you've made any measurement error, you've taken it out by calculating the 4th variable with the other 3. So let's do another one that may not be quite as good. We'll still restrict our population to myopes with the year they were diagnosed. And this time, let's look at, it asks run descriptives. Nope, it doesn't. Oh, yes, it does. Before we do our regression, we're going to look at our descriptives. And we are going to look at, we're going to start with spherical equivalence. I hadn't written that in. Let's see. Spherical equivalence, which is right here. Relative peripheral, this is relative peripheral refraction. Remember, that's using the Grand Seiko, that's calculating their peripheral refraction and subtracting the central refraction from that. That's relative peripheral refraction. We'll put in sex, gender, whatever. VCD, vitreous chamber depth, anterior chamber depth, and lens thickness. Now we're not going to add mean axial length because we just showed that's exactly the same. These guys would it would just confuse it because these are all completely sharing the same thing. So we're just going to see if any one of those has a separate kind of effect rather than the overall. I'm going to put in Gauss strand lens power and calculate it. Now, I'll be honest with you, I thought these two would give you the same answer, but it turns out that we'll see that they don't. We want corneal power, and might as well stick in lag, accommodative lag at 4 diopters. And actually, these are the point of this is just to get these descriptive statistics. Run compute for. So the only thing you have to do with this is just upload this table in your Word document. Remember, all answers have to be in the Word document and numbered by question. Okay, the next question is run a regression model with spherical equivalence as the dependent variable. So we have analyze, regression, linear, reset, spherical equivalence as a function of, and we're going to use these variables up here, and we've already put in spherical equivalent as the dependent variable. So we want to add relative peripheral refraction, sex, VCD, which is the vitreous chamber depth, anterior mean lens thickness, the lens powers, all strand and calculated, corneal power, and lag 40. Our statistics, we want collinearity, and we want to save the residuals. So unstandardized residuals are, you predict a value, use your regression equation, you plug in the values you have, you make a prediction, and then for the actual value, its deviation is the unstandard residual. And so we're going to get, for each record, we're going to get the unstandardized residuals. All right. Okay, what does that show us? So what do I ask for here? Run a regression as the dependent statistics at collinearity. Use the same variable as above. Save the unstandardized residuals will show up in the last column of the data set. What was the overall R squared? Overall R squared is 0.464. Okay, so this model with these variables has accounted for 46% of the spherical equivalent variance. Okay, write the regression formula for the previous model. Okay, let's look at our output. So we get the ANOVA. Regression is what the model is information about regression. Residual is about the error. We'll get more into this when we talk about analysis of variance, but the mean square at 3.34 divided by 0.124 gives us an F of 26 and a significant, highly significant p less than 0.001. Okay, now our coefficients. What is this table? This is an important table. When you are building your model, the constant, that's the intercept, a plus b1 x1, this is b1, this is b2, this is b3. Actually, this is x1, x2, x3. This is over here is b1, b2, b3. So you're going to have y, which is spherical equivalence, equals the intercept plus minus 0.085 times the refractive error. And I'm asking you to do the mean, so you go to your descriptive statistics, and the mean refractive error was 0.4511. So you substitute 0.4511 as the x, and to be is minus 0.085. And so you put in the intercept, you plus that, you plus this times what the value is for 6, you plus this, which is a minus number, times the value for vitreous chamber depth. You do that all the way down. And you add all those things up. It's usually best to copy this into Excel and futz around with the formulas so you can just sum them all up because they're all added up. So in one, here, let's see, copy, Excel, put that in here, paste, and then you can kind of move these guys over one, and you can plug in your X values from the descriptives. Unless the order is the same, be careful, the order probably isn't the same in the descriptives. You put those numbers in there, and then, let's move it over to another one. Then you take this number times for this cell, say 1 is, the intercept is 1. Let's say equals 1 times that, and you copy that all the way down. So it multiplies the coefficient times the x, the mean x in this case, value. But you can do the same thing if you want to find what the predicted value is for an individual subject. We're just doing it for the mean. Then we can, down here, just say equals sum of all of these values once they're calculated. And that's your predicted spherical equivalence. That'd be a pretty high hyperhope. But notice all these are minuses, so you're starting at 46 and you're subtracting all the values from this. Hopefully it'll be a little bit more reasonable number. And let's see. So the question 9 is just write the formula. Number 10 is using the means and find the predicted value. And then I want you to compare the mean spherical equivalence, this mean right here, to the mean we got with the descriptive statistics, which was not that. Oh, here they are. Descriptives. The overall mean was minus 1.399. For at the time they were diagnosed, the year they were diagnosed, the average kid had a minus 0.3999 degree of myopia. Now see how close you get to that when you put in the means. All right. They may or may not be the same. You'll see. All right, the regression using the means. Okay, check collinear statistics, tolerance, and various inflation factors. Which factors were out of bounds for VIF? What does this mean? All right, let's go to our regression equation. And here are, this is not the right one. Here we have our tolerance and our various inflation. Now the tolerance, we want to see values greater than usually 0.3, because this means that relative peripheral refraction accounted for 83% of the variance of it. So if relative peripheral refraction was completely independent by itself, adding a little bit, not necessarily all of it, but a little bit of spherical equivalent, this variable would account for 83%, which means that 17% is shared with these other variables. And gender, this variable accounts for 84%. So whatever sex has to do with myopia, it stands on its own with 84% and only 16% is shared with others. Vitreous chamber depth, that has a problem, and notice its variance inflation factor is considerably over 2. So what that means is that other factors here are contributing. So it is not doing the job by itself. There's others that are like it. Anterior chamber depth and so forth. You can see. So so this variance inflation factor, what is that? And it's inflating the variance more than it should. And our criteria there is 2. If you're greater than 2, it's not good. All right, use descriptive statistics to calculate the variance of the residuals. Okay, so, and the variance of spherical equivalents. So what are they? So if we look at we calculate the variance of, I guess I didn't do this yet. Let's see. Analyze, descriptive, reset. We want to look at spherical equivalents. We want to look at our variance, which is the last column, unstandardized residuals. If we look at our data here, that's not what we want. So we have to go this way. Data. If we slide over to the end, here we've done this before. This was the last time. This was a practice run earlier. You can see that here's the residuals. Now, it only calculates for those values that were selected. So if you go down, you see some. And this is the deviation between the predicted value and the residuals. Probably should have had you do both the unstandardized predicted and unstandardized residuals, and you could see that this value, actually it's kind of, is what the difference is for the actual spherical equivalence minus the predicted gives you this. Okay, so what's the variance of this? Did I do it yet? Did I get distracted? I got distracted. Here we go. So we have spherical equivalents, we have unstandardized residuals, we say OK. And notice for unstandardized residual, the mean is 0. That's because that's the idea of least squares. Things are balanced on both sides, both plus and minus around the predicted. So the mean residual is 0. The standard deviation is 0.347. Now, you can copy this table and put that into Excel too. Over here, paste, and then what is the variance? Pause as you think. The variance is the standard deviation squared. That's just its definition. It's before you do this, when you do the calculations, before you do the square root. Okay. So our unstandard deviation residual, that is, this is the part that isn't predicted by the model. That's 12%. And the spherical, the standard deviation of spherical equivalence is 22.22. I said percent down here, I didn't mean it. 12. Okay, now, so you're to tell me those numbers. Then what else do we have? In the regression output, what is the ANOVA residual mean square? All right. So our regression ANOVA right here, there's this thing called residual, and that's 0.124. That looks a lot like the variance 1205. Now, there is rounding error in this. Who knows where the rounding error comes from? But that's basically the same number as this. So the variance of the unstandardized residual, as we calculated it, we went down that column of numbers in the data sheet and we calculated their standard deviation and squared it. We got the same answer as this part of the residual. And that's because the residual is the error, and what we have is regression. This is the model. This is how much the model predicts. And it was 3.34, and you divide 3.345 by 0.124, and you get an F. And the probability of finding this statistic, if there was no relationship between spherical equivalence and those other variables, the probability of finding that statistic as big as 26 or greater is p less than 0.001. So this is the probability of finding this statistic if the null hypothesis is true. And the null hypothesis is that there is no relationship between spherical equivalence and any of these variables. And it's really, really small. Very unlikely that the null hypothesis is true. Okay, now let's go back to our little spreadsheet here. We have the variance of spherical equivalence, and we have the variance of the unstandardized residual. And if we divide the residual by the variance of y, we see that the residual accounts for 53% of the variance of spherical equivalence. Now, in our ANOVA table here, we have two things that count for all the variability. We have the error and we have the model. So, to get to the model variance, we just take 1 equals 1 minus 0.53. And that's 46. The proportion of variance accounted for, the proportion of the y variance, the variance of spherical equivalence, accounted for by the model is 46. So what is that equivalent to? Well, that's equivalent to r squared. So let's look at this again. So we could also say if we took this variance and subtracted out the residual, we would end up with 10 is the proportion of the variance that's accounted for by the model, and equals 10 divided by that is also 46. So you can either get to the proportion by going through the residual or going through this other path. And the bottom line is the r squared is the proportion of variance in spherical equivalence that is accounted for by our regression model. Okay, I hope if you think about that you understand a little better the nature of r squared. So we did that, and that was 14 and 15, questions 14 and 15. All right, so there you have it. Good luck. Let me know if you have any questions.